Hello, good morning, everyone. I'll be talking about air quality and the associated problems and how we can optimize the sensor placement for them. I'll be starting off with the motivation. Now, due to air pollution, which is a massive problem in Southeast Asia, there are about 7 million plus deaths reported. Some of them are direct, some of them are indirectly linked to air pollution. Contrast this with malaria, HIV, road accidents. If you combine all of them, that is still lesser than the amount of deaths attributed to air quality, majority of which come in the low and middle income countries. If we specifically talk about India, we have about 600 air quality monitors for a population of about 1.5 million people. Now, if we compare this to the other countries, we'll see a massive decrease, massive reduction in the amount of sensing. But important, if you look at the sensors first, we can notice that these are primarily in the urban centers, which leaves a massive amount of rural population under monitored. If we were to compare the amount of sensing across the different countries, for the US, China, we have about 5,000 air quality monitoring stations, whereas for India, Germany, and UK, they're on the order of 3 to 500. But if we compare it on a stations per 1,000 kilometer square area, that is where we again see that some of the countries like India have a much lesser amount of sensing available. Now, the obvious answer should be just install more sensors, but it is not that easy because each sensor can cost on the upwards of about 500K US dollars. That is just the installation, the maintenance, the year long, the across multiple years. That turns out to be much more expensive. So therefore, in this paper, we are trying to address the question, where should we be installing the sensor so that we can get the maximum benefit out of it? We'll pose this as a computational problem now. Given a limited budget of K new sensors, where should we place them so that we can get the maximum information in the entire region? And to put it more mathematically, we'll say that if we have XC as the existing set of sensors, X pool is the candidate set of locations from which we can install sensors, XT, which will be the entire country or the entire continent over which we want to predict and get good information, and K is the budget for the new set of sensors. So we will be choosing K new sensors from X pool locations. In this diagram, I'm showing X pool to be on a grid of about 11 kilometers. Now, this would require optimal sensor placement, which has two facets. The first, we need a surrogate model which predicts the values at the locations as well as the uncertainties. The second, once we have those values as well as we know the location, latitude, longitude of a sensor, we'll score the different locations, different pool locations to see which of them is most likely to give us the maximum benefit. So this is a classic active learning setup, which we are posing in the optimal sensor placement routine. We can start off with a very simple acquisition function, which is a commonly used baseline, which is just random. We will just choose K sensors randomly amongst the pool. Surprisingly, for a lot of problems, the random acquisition works quite well. So this is just closing your eyes, putting sensors at the map K different times. There is no optimization involved. The second one, which is very commonly used, is maximizing the variance. Here we'll choose the locations where we have the maximum variance in the predictions. So this is very fast method because we only need to look at all the pool points once. Amongst them, just choose the K which have the highest variance. So therefore, this is order of K. The third one, which is the most commonly used acquisition method and the best one, is known as mutual information. So this method says that let us put a new sensor Y new, X new, comma Y new, sensor location X new, and the value is Y new. If I put this sensor, how much information do I gain on the rest of the entire grid on which I want to make a prediction? So this has two terms. The first one will remain constant. So therefore, this question about maximizing the information gain would also lead to minimization of the right-hand side term, which is what we'll optimize. So if we compare these two, mutual information versus max variance, both of them will be optimizing for some specific criteria. Interestingly, for Gaussian outputs, the entropy that we were looking for forward is proportional to the log of sigma square. So in both of these terms, we'll see a variance-like term. But the important thing is that for mutual information, the variance is computed over the target region, whereas for max variance, it's computed over a single point, and we maximize that. Now, if we were to use this objective in its exact method, this would require choosing k sensors out of n locations, which is n choose k, which is prohibitively expensive. Therefore, the literature has used greedy variants for this, which is you will, in a simple sense, you will loop over the sensors k times and then choose the one which maximizes the mutual information. Now, importantly, even this has a computational complexity of nk, where n is the number of pool points, k is the number of sensors. For a large region, this will also be computationally infeasible. So this is where we will pose our challenge. We want the speed of max variance. We want the quality of greedy mutual information, but we want both of them together. So therefore, we propose our method, gradient descent mutual information. It's a very simple idea. Typically, greedy MI and similar optimal sensor placement papers would look at a grid and solve the problem in a discrete setting. Whereas for our approach, GDMI, we will directly learn the coordinates using gradient descent, which will maximize the mutual information. So we don't have to do a discrete lookup. Therefore, the complexity is just order of I, where I is the number of iterations we run our algorithm for. So we'll be directly trying to learn the latitude and longitude, which is x nu for k sensors. So k into 2k number of variables we're trying to learn. And we're trying to minimize the average variance over the target region, which is the objective which we saw earlier. For the surrogate model, we had a few choices like Gaussian processes. We ended up using neural processes for the flexibility that they provide, and we didn't have to use very sophisticated kernels. We could directly get a lot of complicated non-stationary behavior directly fed into the model. So we ended up using the transformer neural process variant as a surrogate model. Importantly, when we looked at the surrogate model's performance over the target region, not only was it the best in reconstruction over the entire grid, so given latitude, longitude, if you're trying to predict the PM 2.5 or the pollution over the entire grid, the transformer variant was the best, and it was also the best in terms of getting the uncertainty via the negative log likelihood metric. Now, if we come to the metrics, on the first experiment, we wanted to see how our method would perform compared to greedy MI, random and max variance. Random and max variance are always going to be very quick to compute. Greedy MI works, is computationally feasible for a scale like this. This is a large Indian state. To give the context, this state has a size of about the size of Germany, and it has about n equal to 308 candidate locations over which we could have chosen k sensors. So importantly, if we see that our GDMI approach, shown in blue, is quite better than random and max variance, it is almost approaching the greedy MI, but at a significantly faster time, inference time. If we scale the experiment to pan India, where now the n, which is the number of pool points, is on a scale of 20,000, importantly, the greedy MI approach is not computationally possible. I think if we remember, this would have taken about 65 days to run that experiment, whereas this experiment with our approach was done in a matter of minutes. So this is significantly better than max variance. And importantly, as we were increasing the number of sensors, the gap kept growing between our proposed GDMI approach and max variance and the random baselines. So we look at the results qualitatively. We can see that the max variance shown in blue ends up installing a lot of sensors on the periphery, which do not necessarily improve the performance. Whereas for GDMI, you can see that this location, the sensor placement is much more central. So this is a known fact between mutual information and max variance. This is not our contribution, but our contribution was looking at the converting the problem from a discrete to a continuous variant. If we compare from a scalability perspective, as we increase the number of pool points, we can see that the mutual information method, which is the greedy mutual information method, its runtime will grow, whereas for our method, it remains independent. So therefore, you can discretize the grid in as many high resolution as you want, and you'll still get very good performance. So if we want to see going forward, firstly, the current method was focused only on reconstruction quality. But think of this as a lot of sensors I showed were clustered in the urban centers. So what if we had another metric which was looking at the environmental risk to populations, or the inequity in the sensor placements? Do we need more sensors in rural areas? So if we can modify our objective, include such weightage by population, by the pollution content, or by health vulnerability, we can have the placement which is much more equitable. Going beyond the current set of sensing, we can also now consider a lot of low-cost sensing which is available, so which will introduce new important caveats into the problem. The high-cost sensors will be very accurate, but very expensive, so we cannot place a lot of them. The low-cost sensors will show a lot of noise, which can often also be heteroscedastic in nature, but we can place a lot of them. So how do you combine the high cost as well as the low cost sensors? A lot of countries have this mobile sensing platform. So you can put these air quality monitors on buses, on trains. So we can also then leverage these networks. And we also want to look beyond just PM 2.5 and look into other pollutants. I also want to place our work in the context of the broader scheme of things we are doing in the context of air quality. So we are also looking at mapping out emissions using satellite imagery, figuring out the different sources, formal and informal sources of pollution, which then get fed into the modeling stage, which is currently generally chemical transport models, which is known as WRF-like models. So we want to replace them with neural emulators. Once we have that, we want to do sensing, which is equitable, and optimal sensor placement, which is today's paper. Eventually, we want to leverage, and we are leveraging LLM-like models to give out the information in an easy to access format for the stakeholders. So if I conclude, we propose GDMI, which is the first gradient-based MI formulation for sensor placement. It provides significant scalability benefits compared to the discrete problems. The benefits primarily come from posing the problem as a continuous problem. We also find that the quality is largely preserved compared to greedy MI, and it is now ready to be deployed at a large scale. With that, I'd like to end the talk. I'd also like to mention that my PhD student Zeel is sitting here, who will also be presenting the poster in about 30 minutes. And we are always open for PhD postdoc interns researchers. Thank you.
Okay, thank you for the great talk. Are there any questions? Okay, I have a question. Could you please turn to the page 19? Yes, I can see here you predicted the PM 2.5 and uncertainty. I'd like to know what is the uncertainty, what does the uncertainty mean in this case?
So we'd assume the uncertainty for the quantification of the uncertainty, we'll assume a Gaussian distribution on the prediction. So therefore, we'll not just predict the mu, we'll also predict the sigma. So that is how we're getting the uncertainty. In very simple terms, we can have two output nodes coming out of a neural network, one of which predicts mu, the other predicts log sigma. And that is the neural process variant that we've used.
Okay, there is no real world case.
Sorry?
There is no real world case.
So the data is coming from a gridded data set, which is actually real world data, which has been fed into a model so that we can get the prediction on a country scale, so that we can then use it for prediction on a grid. So it is actually real world data, which has been regridded.
Okay, thank you.